In the heart of this silent desolation, humanity is about to embark on one of its greatest engineering challenges. Here, where there's nothing but rocks and soil, we will build a structure that harnesses the power of the stars to light millions of homes. Before laying a single stone, the battle with geology begins. Teams of experts probe the Earth's depths, searching for hidden fault lines and analyzing soil density to ensure eternal stability for this coming giant. There's no room for error here. This ground must withstand the most violent earthquakes in recorded history. The calculations here aren't based on probabilities, they're based on the worst possible catastrophic scenarios. The blueprints aren't mere drawings, they're a symphony of millions of interlocking parts. Every pipe, every valve, every bolt has been calculated with physical precision that challenges the limits of human understanding. The challenge isn't just in construction, but in cooling. We need a massive water system to tame the atom's fury, and the water intake design requires incredibly complex hydraulic engineering. Meanwhile, a fleet of heavy machinery arrives, an army of steel, ready to reshape the geography of this place, signaling the beginning of the excavation epic that will transform this land forever. We start digging deep, not meters, but through ancient geological layers until we reach bedrock, that solid foundation that will support millions of tons of weight. The earthen walls must be reinforced immediately. Sprayed concrete forms a temporary shield, preventing the excavation from collapsing on the workers, who look like ants at the bottom of this artificial valley. Since groundwater is the primary enemy of foundations, giant pumps operate around the clock to dehydrate the site, transforming the muddy bottom into a dry, solid work platform. Every centimeter of soil undergoes nuclear density testing. If the soil gives even 1 millimeter under pressure, it could mean disaster down the road. Safety culture here isn't a slogan, it's a doctrine. One simple mistake at this stage could fester into a crack in the nuclear shield decades later. So we don't rely on ordinary dirt, we import engineered fill, a special blend of gravel and sand compacted precisely to absorb any ground vibrations. Meanwhile, giant rollers compress the earth with tremendous vibrational force, forcing soil particles to bond until they become hard as rock, ready to support the weight of a skyscraper. At point zero, surveyors use laser precision to mark the reactor's engineering center. From this imaginary point, all measurements will launch the world's most complex structure. As the sun sets, the stage is ready. The excavation phase ends, and it's time to pour the foundations that will last thousands of years in the earth. The first layer is the leveling course, a thin concrete layer that isolates the steel from the soil and provides a clean slate for engineers to start shaping the reinforcement framework. Here lies the genius of seismic engineering. Massive rubber and lead pads isolate the building from the ground, allowing it to dance with earthquakes instead of shattering. The reinforcement bars here aren't ordinary. They're as thick as a human arm, made from special steel alloys to resist rust and the enormous tension from heat and pressure. Workers weave a steel grid so dense you can barely fit your hand through, creating a cage that will hold the concrete and prevent cracking no matter what. The iron density here exceeds 440 pounds per cubic meter. Because we're not building an apartment building, we're building a nuclear fortress that must be harder than the mountain beneath it. Then comes the mat foundation, a single continuous piece of reinforced concrete meters thick, designed to distribute thousands of tons of load perfectly evenly. During the Great Pouring Night, a fleet of trucks lines up like an advancing army. Once pouring begins, it can't stop. The concrete must be one homogeneous mass. As pump arms stretch out like giant tentacles, pumping an endless stream of gray mixture, the coordination must be Swiss watch precise to avoid cold joints. The secret lies in vibration. Workers use mechanical vibrators to force the liquid concrete into the tightest spaces between the steel, expelling any air bubbles. Because concrete's chemical reaction generates heat, in these massive blocks, temperatures can reach boiling. So we bury cold water pipes inside the pour to cool it from within during 48 hours of continuous work, with shifting crews as the sun rises and sets. The concrete flow never stops for a moment, a race against time and chemistry. Finally, the base is complete and covered with wet burlap to ensure slow hardening. This foundation will be the platform on which the reactor stands for a century. On top of the concrete, we place the containment liner, a layer of carbon steel welded precisely. Its job to ensure not a single gas atom leaks from the building. Every weld here undergoes radiographic inspection, no porosity or cracks allowed. This steel is the last line of defense between radioactive materials and the outside world. Then the walls begin rising. Curved steel plates form the internal mold for the building, beginning to shape the nuclear island that will contain the reactor. Before pouring the walls, we must bury a complex network of pipes and electrical conduits, because once concrete is poured, access becomes impossible. Precision is law. We use self-climbing formwork, a hydraulic system that raises the forms as the building grows, enabling rapid, safe construction of soaring walls. Meanwhile, in field laboratories, concrete samples are crushed under enormous pressure to verify they've achieved required strength. Power is measured in megapascals. At the lowest point, we install emergency drainage systems to ensure any liquid leaks are caught and treated before reaching the environment. The copper grounding network extends under the foundations, protecting sensitive equipment from lightning strikes and discharging any electrical charges threatening control safety. We build a core catcher, a special zone made of high-resistance thermal ceramic designed to contain melted fuel in the worst reactor meltdown scenario, with sacrificial concrete engineered to melt and blend with nuclear fuel to reduce heat and prevent groundwater contamination, a passive safety system requiring no human intervention. As the walls rise to touch the sky and trucks below become tiny toys, the thickness of each wall exceeds 5 feet of reinforced concrete. We don't use conventional connections. Instead, we use threaded mechanical joints, ensuring continued tensile strength through the steel bars as if they were one unbroken piece. Quality inspectors circulate like shadows, measuring the distance between bars in millimeters. Any deviation means stopping work and immediately reassembling. To accelerate construction, we use prefabricated units, massive blocks of steel and concrete prepared on the ground, then lifted and assembled like giant Lego pieces. The crane dance in the site sky requires precise wireless coordination. Arm collisions are forbidden, and loading weights over sensitive areas is governed by strict calculations. Steel sleeves penetrate the walls as the only passages for cables and pipes, which must be sealed completely to prevent radiation leaks through these gaps, leading to the biological shield wall, thicker and denser, whose job is protecting people from deadly neutrons released from the reactor's core during operation. Thus, the lower fortress is complete. Foundations are solid, walls are taking shape, and now we're ready to receive the beating heart, the project's heaviest and most dangerous equipment. To lift the incoming weights, we need a mechanical monster, the world's largest ring crane, capable of lifting thousands of tons with surgical precision. When the heart arrives by sea, the reactor pressure vessel, a single piece of forged steel with no longitudinal welds, ensuring maximum safety, the vessel is transported with extreme care on a multi-wheeled trailer. Hundreds of tires distribute its massive weight across the road, moving at a snail's pace toward the construction site. At the moment of truth, the giant crane's cables tense, and the hundreds of tons vessel rises into the air, suspended between sky and earth in a breathtaking scene. Then, slow descent begins into the building, where the available space around the vessel is just centimeters. The crane operator guides the load based on laser instructions until the vessel settles on its supports. Here it will remain for 60 years, embracing the nuclear reaction and withstanding unimaginable pressure and heat. Then, the steam generators arrive the lungs through which the reactor breathes. These giant heat exchangers will convert atomic energy into steam that drives turbines. Raising and installing these tall cylinders vertically requires exceptional skill, as they must connect to the reactor vessel with perfect precision, ensuring unobstructed water flow. Meanwhile, welding of the primary cooling circuit begins. These massive steel pipes will carry irradiated water, and welding happens automatically to ensure metal uniformity with no bubbles. Every millimeter of weld undergoes X-ray imaging in detailed pictures, revealing what's inside the metal. If a defect the size of a pinhead is found, the weld is scraped and redone. Next, we install the pressurizer, a tank preventing reactor water from boiling despite temperatures exceeding 600 degrees by maintaining enormous pressure. After equipment installation, we build internal concrete walls around it that support and protect the equipment and form isolated rooms for each primary circuit component. We also install the polar crane supports at the top of the circular wall. This crane will live inside the dome forever, serving maintenance operations and future fuel changes. Then, we raise the crane bridge, a massive metal piece extending across the building's full diameter, rotating smoothly on a circular track at the wall's top. Meanwhile, on the ground, we assemble the steel-lined dome by welding hundreds of plates to form a perfect hemisphere, the ceiling of the nuclear world. In a magnificent scene, the crane lifts the steel dome, weighing hundreds of tons, appearing like a giant flying saucer, slowly soaring to cover the reactor building. Once the dome is in place, perimeter welding begins. Now the building is completely closed inside with a tight steel layer, ready for the next phase. But steel alone isn't enough. so workers begin covering the dome with dense layers of reinforcing bars. We'll build a concrete dome over the steel dome and plant special cables for pre-stressing inside the walls. These cables will later tense the building, enabling it to withstand enormous internal pressure without exploding. Concrete continues rising around the steel lining as the outer wall grows thicker and taller, becoming the impregnable fortress, protecting the reactor from missiles and aircraft. The designs underwent wind tunnel testing. The circular shape isn't just for beauty, but to disperse wind and hurricane forces, making it one of the most structurally stable geometric shapes. Pouring concrete on the dome's sloped surface challenges gravity, so we use special low-flow mixtures, pouring them in symmetrical circular strips to maintain load balance. After concrete hardens, bundles of high-strength steel cables are fed through hollow channels in the walls and dome to begin post-tensioning. Hydraulic presses pull the cables with hundreds of tons of force, compressing the concrete together. This makes the building incredibly strong. After tensioning, we inject the ducts with liquid cement material to protect the tensioned cables from rust and fix them in place forever. Then we install the access gates, which are not ordinary doors, but double-sealed steel pressure chambers that ensure no contaminated air escapes during worker entry or exit. Next to the reactor rises a different structure, the turbine hall, a massive steel framework designed to accommodate the rotating equipment that will generate electricity. Beneath the turbine platform, we install the condensers, giant boxes containing thousands of tubes where steam returns to water and completes the closed life cycle. We use titanium pipes here to resist saltwater corrosion, where thousands of connections require extreme precision, because any seawater leak into the system could damage the reactor. Then we raise the low-pressure turbine rotors, giant blades designed with precise aerodynamics to extract every last drop of energy from expanding steam. The turbine shaft is aligned with lasers. The line must be perfectly straight to a fraction of a millimeter, because this shaft will rotate at 1,500 revolutions per minute while weighing hundreds of tons. After that, we install the electrical generator in both its stationary and rotating parts, where mechanical motion transforms into a flood of electrons that will light up cities. The generator connects to the main transformers through massive insulated copper buses that will carry enough power for a small nation. On the shore, we build the pump station, massive concrete structures containing filters and giant pumps to bring cooling water from the sea or river, extending enormous intake pipes underground where the pipe diameter could fit a truck inside. This ensures an entire river of water flows through to cool the condensers. We also install rotating screens to protect marine life and prevent debris. The technology here balances the reactor's needs with environmental preservation. Then comes safety, safety above all else. We build backup diesel generator buildings, separate fortresses housing massive marine engines, ready to operate if power cuts out, with enormous fuel tanks underground, capable of running the generators for days or weeks. The reactor must stay cooled, even if the outside world collapses. Inside, we begin installing the information arteries, miles of metal cable trays weaving through corridors, carrying power and data to every corner of the station. Pulling heavy cables is grueling work. Teams labor in perfect coordination, threading these black copper serpents without scratching their sensitive insulation. We carefully maintain physical separation between safety systems. System A cables are completely isolated from System B, so if fire destroys one, the other continues working as if nothing happened. We seal gaps with fire-resistant materials, ensuring flames cannot spread from one room to another, containing any danger before it spreads. The ventilation system isn't for comfort, but safety. Massive ducts maintain negative pressure inside the nuclear buildings to ensure contaminated air never escapes. High-efficiency filters and activated carbon filters catch any radioactive particles floating in the air, purifying the reactor's breath before release. Now we move to building the spent fuel pool, a deep basin lined with stainless steel, where spent fuel rods will rest for years underwater, cooling and becoming less radioactive. We test the basin for leaks, filling it with water and monitoring the level with microscopic precision, because not a single drop of loss is acceptable in this critical pool. Then, we install the fuel handling machine, a massive robot moving above the basin and reactor, designed to lift delicate fuel rods with supreme precision and smoothness. In the main control room, the station's brain, we build the raised floor to hide thousands of cables, connecting operators to every valve and pump. Giant screens cover the walls, displaying the reactor's status moment by moment, giving operators complete visibility of every heartbeat in the station's core. Connecting the control panels requires care. There are no random switches here. Every button has a vital function, and the design considers the work environment to reduce human error. Next comes installing the reactor, cooling pumps massive engines with thousands of horsepower, driving water with the force of a waterfall to extract heat from the reactor's core. The pump seals are engineering masterpieces, preventing leakage of extremely high-pressure water around the rotating shaft using complex cooling technologies. Above the reactor vessel, we mount the control rod drive mechanisms. These are the reactor's brakes and must drop their rods and stop the reaction within seconds. Welding the control rod guide tubes requires surgical precision to ensure the rods stay perfectly straight, because any bending could obstruct the nuclear brakes when needed. We also install hydrogen recombiner units, devices that work without electricity, transforming hydrogen rising during accidents into water and preventing explosions. We equip the chemistry labs, where water samples are analyzed daily to adjust chemical balance and prevent pipe corrosion. Since the fortress needs walls, security systems, thermal cameras, and anti-intrusion gates surround the site, making it an impregnable stronghold against external threats. The paint here isn't decorative, but special epoxy coating that's easy to decontaminate and prevents concrete from absorbing any liquids. We test the bridge crane with enormous water bags, loading it with weights exceeding maximum capacity to ensure it won't fail when lifting the reactor vessel. Then comes the cold hydrostatic test. We fill the system with water and raise pressure beyond operating levels, searching for any leaks, any weakness, any valve that doesn't seal properly. Inspectors run their eyes and hands over the pipes. At this pressure, even a water droplet has a sound. It's the first stress test for the station's arteries. After that comes the hot functional test, where we operate the giant pumps. Water friction raises temperature to operating levels without nuclear fuel, making the station alive mechanically. Then we test the turbines with steam generated from pump heat, and the blades turn for the first time. The electrical giant awakens from its slumber. In emergency simulations, we test safety systems, suddenly close valves, and monitor automatic systems response, as they should work like the body's natural defenses. Then comes final cleanup of the reactor core, because any dust particle or forgotten wire could be catastrophic. So we clean the vessel to absolute purity. When fuel arrives, armored trucks carry fuel containers holding energy equivalent to millions of tons of coal compressed into small capsules. We inspect the new fuel, where shiny zirconium rods contain uranium pellets that must be completely scratch-free to ensure cladding integrity. We first store the fuel in the dry water pool, handling it very carefully even though it's not yet highly radioactive. Loading the core begins. Underwater, the machine transfers fuel rods, one by one, into the reactor vessel in a precise, geometric arrangement. The loading pattern is physically studied. Fuel distribution determines burning efficiency and heat distribution, with each rod having its designated place in this matrix. After closing the cover, we lower the massive reactor head and tighten the giant bolts with synchronized hydraulic equipment. The core is now sealed and ready. In the control room, anticipation silence reigns at the first critical moment, as we slowly withdraw the control rods to begin the chain reaction. At the atomic level, neutrons begin striking uranium nuclei, splitting the atom and releasing energy and heat, ejecting new neutrons in a cascade. The reaction has started. The neutron flux curve rises. The reactor is now critical, meaning the reaction is self-sustaining. We've awakened the sun inside the concrete fortress. As heat transfers to water, water turns to steam, and steam begins driving the turbines. The rotors accelerate to their operating speed. Synchronizing with the grid requires matching the generator frequency with the national grid frequency with perfect precision. The connection moment is the moment a new power source is born. The circuit breakers close, electricity flows, and cheers erupt in the control room. Years of planning and construction have culminated in success, and the station pumps life through the wires. Outside, transformers hum with the sound of power, and high-voltage lines carry gigawatts of clean, carbon-free electricity to distant cities. This reactor will operate day and night, summer and winter, continuously as a reliable power source, independent of wind or sun, dependent only on the universe's physics. But the work doesn't end here. Maintenance teams remain vigilant, monitoring every indicator, inspecting every device to ensure this miracle continues safely for decades. Environmental teams monitor nature around the station. Air, water, and soil all undergo continuous testing, proving nuclear power can be environmentally friendly. Cooling water returns to the sea, warm and clean, exactly as it entered, without touching any radioactive materials, preserving the natural life cycle. In the training center, a new generation of operators learns the art of running the reactor. Knowledge passes from generation to generation, ensuring human expertise continues. The site that was once a muddy hole has become a technological oasis, where buildings stand complete, roads are paved, and the reactor becomes part of the region's fabric. At night, the station sparkles like an industrial jewel, a beacon of hope in a world seeking solutions to climate and energy problems. This concrete dome isn't just a cover, but a symbol of protection under which humanity tames the universe's most violent forces for peace and prosperity. The electricity generated here lights operating rooms, runs factories, and heats homes like a hidden lifeline, supporting modern civilization. For the thousands who built it, this isn't just work, it's a legacy. They'll tell their grandchildren they helped build this giant that will serve future generations for 60 years. And this reactor will witness the world's changes while remaining steadfast, quietly, and reliably pumping power. Even at the end, there's a plan. When retirement comes, the reactor was designed to decommission safely, returning the land to nature, completing the cycle of responsibility, from dust to atoms, from blueprints to reality. The journey of building a nuclear reactor is a story of human ambition without limits. A symphony of steel, concrete, and human intellect, brilliant proof that through science and collective work, we can perform miracles. And so, the heart continues beating, the light continues shining, and here, where mind met matter, we made our own sun. In every watt of electricity lies a story of struggle, engineering, precision, and vision for the future. This is it, building the nuclear reactor, the end of the journey.